Prerequisite skills, section number 1, looking at some algebraic expressions, mathematical models, and real numbers. In this lesson, we'll look at evaluating algebraic expressions, use mathematical models, find the intersection of two sets, find the union of two sets, recognize subsets of the real numbers, use inequality symbols, evaluate absolute value, use absolute value to express distance, identify properties of real numbers, and simplify algebraic expressions. The majority of Chapter P should be some Algebra 1 and Algebra 2 review. There will be a few new topics intertwined in there, so please don't overlook some of the new things with thinking you remember and understand all of the old review topics. So looking at an algebraic expression, it says if a letter is used to represent various numbers, it is called a variable. It varies. A combination of variables and numbers using the operations of addition, subtraction, and multiplication or division, as well as powers or roots, is called an algebraic expression. Evaluating an algebraic expression means to find the value of the expression for a given value of the variable. The expression b to the n is called an exponential expression. In terms of some exponential notation, it says if n is a counting number, 1, 2, 3, and so on, b to the n, the b is your base, the n is the exponent or power, and a way to remember how you evaluate exponents is whatever the base is gets multiplied n number of times. So it tells us that b appears as a factor n times. So b to the n is read the nth power of b, or b to the nth power. Thus, the nth power of b is defined as the product of n factors of b. The expression b to the n is called an exponential expression. Furthermore, b to the first is equal to b. One common mistake with exponents is when you have a b to the 0 power. Do you remember anything to the 0 power has a single answer? Do you remember what that was? Well, b to the 0 power would end up equaling 1. So even if I had something like 5 to the power of 0, anything to the 0 power is 1. So a little Algebra 1 review in there. The order of operations, it says the product, or to perform operations within the innermost parentheses and work outward. If the algebraic expression involves a fraction, treat the numerator and the denominator as if it were each enclosed in parentheses. You have to know what you're doing in terms of the division. A fraction bar is a division. You need to know what the numerator is. You need to know what the denominator is before you do that division. So order of operations wise, you're starting with your parentheses. Number 2, it says to evaluate all exponential expressions. So that's our exponents. Perform multiplications and divisions as they occur, working from left to right. So we have our multiplication and our division. And we also have to, in step 4, perform our addition and subtraction as they occur from left to right. And our short little acronym is our PEMDAS. Please excuse my dear Aunt Sally. Basic middle school order of operations concepts. So evaluating some expressions, if they tell us that x is equal to 13, we take out the variable, we replace it with the number, and we follow our order of operations. This stuff should be plenty good and easy. It's kind of middle school math. So 8 plus 6 times, in place of x, we have a 13 minus 3 to the second power. Order of operations tells us we must start within our parentheses. So if we take our 13 minus 3, we end up with 10. So we have an 8 plus 6 times 10 to the second power. We know the next step we need to perform is our exponent. So 10 to the second power, that's going to give us a 100 that we can then multiply by 6 and add the 8. So you'd end up with your 608. I'll go speedy kind of through some of the easier examples and take it a little bit longer on some of the harder, maybe newer stuff. Some formulas and mathematical models. It says an equation is formed when an equal sign is placed between two algebraic expressions. A formula is an equation that uses variables to express a relationship between two or more quantities. Quantities just means how many. Quality over quantity, right? Quality, you want something to be better over quantity, how many of that item you have. So quantities. The process of finding formulas to describe real-world phenomena is called mathematical modeling. Such formulas, together with the meaning assigned to the variables, are called mathematical models. So any of those formulas you can kind of dig through your long-term memory would be a mathematical model. So an example, it says the formula t is equal to 4x squared plus 341x plus 3,194 models the average cost of tuition and fees, T, for public U.S. colleges for the school year ending X years after 2000. Now this book is a little bit older and I'm pretty sure tuition fees are a little bit more expensive than what this model shows, but for the sake of being the book that we're going to use, we'll go with it. All right, so it wants us to take a look at X number of years after 2000. X number of years after 2000. So they're telling us that we have our formula. The formula indicates that for the school year ending in 2015, the average cost of tuition and fees at public U.S. colleges will be how much money? So if X is representing the number of years after 2000, and we're talking about the year 2015, what is X representing? Well, from year 2000 to 2015, X is going to be 15 years. So we're going to take our expression or our equation, plug in our 15, and solve it down. So the amount of tuition we're going to have is going to have 4 times, in place of X, we're going to plug in 15. We'll square that. Add 341, multiply that by 15, and then add in that $3,194. Order of operations, I see some exponents, so we're going to take care of our 15 to the second power, which gives us 225. And then we have some multiplying to do next. If we multiply 4 times 225, that's going to give us 900. If we take 341 and multiply that by 15, we'd have 5,115. Feel free to use your calculator and double check that. If we take our 900 plus our 5,115 plus our 3,194, we should end up with $9,209. Now, something you may or may not be quite as familiar with would be sets. This might be something that maybe, depending on what teacher you had prior to this year, you had an introduction to sets, maybe not, or maybe you had an introduction, but that's long gone. So a set is a collection of objects whose contents can be clearly determined. The objects in a set are called elements of the set. We use braces, those squiggly looking things, to indicate that we are representing a set. So if we have a set with 1, 2, 3, 4, ... that ... is called an ellipse, meaning it continues on beyond that number 5, is an example of the roster method of representing a set. The 3 dots after the 5, called the ellipse, indicates that there is no final element and that the listing goes on forever. If a set has no elements, it is called the empty set or the null set and is represented by the Greek letter phi. That is just a 0 with a slash through it. There's nothing in that set. So our set builder notation, it says the elements of the set are described but not listed. So they have our little squiggly opening, and then there's that X and then a bar and then X. So that's going to read X such that. So X such that X is a counting number less than 6. So they said it's read the set of all X such that X is a counting number less than 6. It says the same set written using the roster method is 1, 2, 3, 4, 5. Now that ends at 5 because it doesn't have that ellipse on the end there. So definition of the intersection of sets. The intersection, if you think of an intersection, that means two things are crossing over each other, right? You have roads, and when you hit an intersection, so where two roads are crossing over each other. So the intersection of set A and B, written as A, and it kind of looks like an upside down U, B, is the element or the set of elements common to both set A and set B. So the intersection where they meet, what's in each set, is going to be the intersection. It says this definition can be expressed in set builder notation as you have that A, that upside down looking, B, is equal to X, such that X is an element of A and X is an element of B. So we are looking that it has to have it both in common. You're looking for that same number in both sets. So it says find the intersection of two sets. So we have in our first set 3, 4, 5, 6, 7. And in our other set, we have a 3, 7, 8, and 9. So our intersection, what are the things that are in common? Well, I see a 3 in both sets, and I see a 7 in both sets. So we would write it in our set builder notation. Do the best you can with your little squigglies. We would put a 3, a comma, and a 7, and then that was really ugly. We'll try again. Right? Practice your little squigglies. Do the best you can with them, right? So 3 and 7 would be the intersection because that is in common in both of the sets. The other kind is the definition of a union of sets. The union of sets A and set B, written as A union B. Now, to me, union is like a whole bunch of people coming together. For instance, there's a teachers union, and so it's the teachers that are kind of coming together as a full group. So A and then a regular looks like a U for union. B is a set of elements that are members of set A or of set B or of both sets. This definition can be expressed in set builder notation as followed. So that A with the union symbol B is equal to X such that X is an element of A or X is an element of B. So it's in one or the other. It might be in both. It's going to be included. Everybody's included. So we can find the union of set A and set B by listing the elements of set A. Then we include any element of set B that have not already been listed. Enclose all elements that are listed with braces. This shows that the union of two sets is also a set. So let's take a look at another example. This one tells us to find the union of 3, 4, 5, 6, 7 with 3, 7, 8, and 9. So I start listing it out from least to greatest. I'm going to take that first set. So I have a 3, which is included in the other set. And then I have a 4, a 5, a 6. I have a 7, which is included in the other set as well. And now I also have, now that I've used all of that first set, I check the second set. What have I not written down yet? I still need an 8 and a 9. So a union, everybody's coming together. So everything is listed. An intersection was what was in common in both of those sets. So another way that you may have seen the word set is the set of real numbers. It says the sets that make up the real numbers, and they use that funny looking R. Sometimes it is like a double staff made into an R. So that's a symbol for real numbers. So the sets that make up the real numbers are we have the set of natural numbers, and that actually kind of looks like a funny looking N. It has like a double staff in the middle there. The set of natural numbers, 1, 2, 3, 4, and 5. The set of whole numbers, kind of a little like how you remember that as a whole number. You have this O, right? O means you're starting at 0. So whole number starts at 0. 1, 2, 3, 4, 5. The best way to kind of remember the difference between the two is naturally, if you're telling someone to count to 10, where are they going to start? Naturally, we go 1, 2, 3. So natural numbers are kind of like your counting numbers. Naturally, how would you count? And then whole numbers gets into that 0. The set of integers is when you're looking at positive and negative whole numbers. So you have that little ellipse and then -5, -4, -3, -2, -1, and then 0, 1, 2, 3, 4, 5, etc. The set of rational numbers is anything that can be written as a fraction. So if you can write it as a fraction, it's rational. Repeating fractions can still be written, repeating decimals can still be written as fractions, so they are rational. So they are any number in terms of a fraction that would end or repeat. You're looking at your rational numbers. So it says, and then the set of irrational numbers, if you remember some irrational, the most famous irrational number would be like pi. Or if you had a square root of a number that cannot simplify down to an integer, like a square root of 5, that would be irrational. It says irrational numbers cannot be expressed as a quotient of integers. So, in terms of those sets, how they work together, the set of real numbers is a set of numbers that are either rational or irrational. So you can't be rational and irrational at the same time. So you're rational or you're irrational. But within those rational numbers, go all the way down to that little green box that says natural numbers. You have natural numbers, which are included with those whole numbers, which are included with those integers, which are included with those rational numbers. And if you're not rational, you're irrational. So let's recognize a couple subsets of real numbers. It says to consider the number or the following set of numbers. It says list the numbers in the sets that are, we're going to look for which of those numbers are natural, which one are whole numbers, which one are integers, which ones are rational, and which ones are irrational. So natural numbers. Natural numbers means that we can have a counting number, 1, 2, 3, 4, 5, etc. So let's take a look. -9, well, that's an integer. That's going to be a negative. We don't see that until we get to integers, so that's not natural. -1.3, we have a decimal. It ends, so that means it could be written as a fraction, which means that that is not natural. We have 0, which is not natural. That's not part of our counting numbers. 0.3 repeated. Repeated means that hopefully you know what that fraction equivalent is, right? It's a 1/3 if you didn't know that. We have a pi over 2. That's definitely not natural because it's pi, right? We have a square root of 9. Well, can that be simplified down? The square root of 9 gives us 3, right? 3 times itself. Well, 3, isn't that a natural number? So our natural numbers would technically be that square root of 9 because it simplifies to 3. Square root of 10, that is not natural, right? That does not simplify down just like we gave that example, the square root of 5. So let's see, whole numbers. We took care of square root of 9, but we know that that's also going to fall in some of these other sets. So let's go back to whole numbers. So we know that square root of 9 is going to be a whole number as well. And then the other thing that we had was that 0, right? That's where whole numbers begin. So integers. Well, natural numbers are whole numbers and whole numbers are integers. That means we have a square root of 9 and we have a 0. What else would be an integer? Oh yeah, we said that -9 is going to be an integer. Positive and negative whole numbers. Don't see any other integers. Well, rational numbers, all of the above are rational, which means we're going to have that square root of 9, we're going to have 0, we're going to have that -9. Let's see what else we got. -1.3. -1.3 means a -1 3/10, which means that that is a negative, what do we got, 13/10. It could be written as a fraction. That means it is rational. So -1.3 is rational. And 0.3 repeated. I kind of already gave you that hint that that is a 1/3. You should kind of know some of your fraction decimal equivalents at this point. I don't want to write 1/3. I want to write the 0.3 repeated. Always write the numbers that they give you, not what they would simplify or change to. So now that we have our rational numbers, we said that -9 was rational. We said that -1.3 was rational. We said 0 is rational. We said 0.3 repeated was rational. Pi over 2, that has to be irrational then. As soon as we see pi, it tells us it's irrational. And then our root 9, square root of 9 was a 3, so that was rational. We got that taken care of. Square root of 10, well, we didn't use that one yet, so that one has to be irrational because you're either rational or you're irrational.